Okay, perfect. So first of all, I would like to thank you for the kind invitation. It's a pleasure to be here. Actually, I think the last time was certainly before Corona, I think 2016 or 2017, I'm not 100% sure. So it's really nice to see Professor Lee again, and I think it also remodeled, I think, this university a little bit. It looks a bit different compared to the last time I visited. So today I want to talk about what we have done on, we call it scientific machine learning with applications in engineering and material science, but I probably will talk only about the applications in engineering, or it's actually more in mechanics, because I think here's nobody who's working really on density functional theory or like ab initio simulation. So I will basically focus only on the solution of partial differential equations. So that is also the outline of my talk. So as I mentioned, actually, I will leave out the last portion and will leave it also a bit shorter, like 30 minutes in that area. So here we use directly machine learning for the solution of partial differential equations. I think maybe many of you have heard the term physics informed neural network. There's this very seminal paper by Raisi and George Kaniadakis published in 2019. The idea is basically to include some physics laws into the loss function. We have also developed our own method. Instead of using the strong form, we have used an energy minimization method. We call it the energy method. There are alternatives like the deep Galerkin, the Ritz method. So these are basically two approaches for the solution of partial differential equations. It's like an alternative to finite elements. Then I want to talk about neural operators here. That there are of course different neural operators, spectral neural operators, Fourier neural operators, deep operator networks, and deep nets. So we have done a little bit of work on that, and that idea was also proposed by George Kaniadakis, the developer of this physics-informed neural networks. And that is not an alternative for the solution of PDEs. It can be seen as a surrogate model. It can be purely data-driven. You can, of course, also include physical laws into the loss function of this deep operator network. Okay, now I can, okay, now this, I think I point rather in this direction because then I don't need to turn back. So I will point in that direction. Then I will show you some of these numerical examples which we have obtained. I have to say, they are maybe not so, from the complexity, too impressive. It basically shows that one can actually solve also partial differential equations with neural networks. But as you can see, this approach is fairly new. And so actually, having said that, the first idea was proposed in 1998 by Lagarde. So that actually goes back for some time. But I think due to the development of GPUs, technology, and also tools like TensorFlow, I think it has now maybe a second spring. So before I want to start our presentation, I want to make also a short advertisement. So we just have published, or the book is, I think, about to appear in September. So I edited the book together with my friend and colleague Jürgen Barthe, called it Machine Learning and Modeling and Simulation, Methods and Applications. So there are different authors who have contributed to different chapters. And we have also another book with Xiao Yin and my postdoc Cosme Anitescu and some Dr. Ravi, who is or has been in the group of George Kaniadakis in Brown University. Actually, that book was supposed to be ready last year. We call it Scientific Machine Learning with Engineering Applications. So that is basically more or less about physics-informed neural networks and maybe also some other topics like uncertainty analysis. Okay, so let me briefly explain the different ideas of pins and in this deep energy method. I just want to have here one slide about the neural network architecture. We use a standard feed-forward neural network. I think most of you have probably seen such a slide very often, so I don't really need to explain that structure. So the idea of this machine learning PDE solver is actually fairly simple. Let's assume you have here unstable. Okay, we have here, let's say, a domain. So you would then put collocation points in the interior of the domain somewhere. You will put also collocation points on the boundary. That is maybe similar to a meshless approach. And then you would simply relates the boundary value problem to the loss function. So assume we have here a partial differential equation of that form. L is a potentially nonlinear differential operator applied to a tensor function u, which depends on the spatial coordinates, maybe also on the time. And then we have here source term on the right hand side. We might have boundary and initial conditions, and optionally we might have also experimental data which you can include into the formulation. I have to say the examples I will show there without any experimental data, because I'm not an experimentalist. And, I could maybe only download data from the internet. And of course, I also would like to mention we can have, of course, multi-physics problems, so we can have also a set of coupled PDEs. And then you would relate now this boundary value problem to the loss function. So we have here a term related to the interior, to the Dirichlet von Neumann boundary conditions, maybe initial conditions if the problem is dynamic, and then also experimental data. Then we have different weights. So of course, how to choose the weights is still like still needs to be decided. There are of course also so-called self-adaptive pins where the weights are trainable, so you would minimize the loss and simultaneously maximize the weights. So basically the weights would increase where the error is then a bit larger, so the system automatically focuses on these domains. And that is all the idea behind it. It's very simple, and there have been meanwhile also a lot of improvements. For instance, you can change the network architecture, you can play with the activation function, the way how to impose Dirichlet boundary conditions. You can also use, for instance, radial basis function networks, which maybe have better approximation properties. So there's a lot of room for improvement. And the alternative to the so-called physics-informed neural networks, which are based on the strong form, is to use an energy minimization method. So like finite elements, it's based on the principle of minimum of the total potential energy. So in this case, the loss function would be the total potential energy, which you minimize. So this has two major advantages. First of all, you reduce the requirement on the differentiability of your basis function. So if you have, for instance, a second order PDE in the strong form, and then you need only the first derivatives in the weak form, or here in this energy minimization approach, you naturally also account for Neumann or natural boundary conditions. And on the downside, of course, we have to somehow evaluate the integrals, where we standardly use Gaussian quadrature. And of course, that works fairly well when we have relatively smooth solutions. And we need also more integration points, because the activation functions used in the network architecture are usually not polynomial. So then another issue is to place collocation points, or maybe Gaussian points in the domain. So what we have done here, we have like an adaptive strategy. Of course, the number of collocation or training points needs to be somehow correlated to the network architecture. So we start here with an initial training set, which is relatively coarse. Then we train the network, we evaluate the residual on a larger set of points, and where the residual values are large, then we basically add new collocation or training points, and then we retrain the network, starting with the weights and the bias from the previous step, so obtain faster convergence at the subsequent steps. So we can, of course, combine this approach to any geometry definition. We can use a point cloud in case we have like such data. We can also use CAD compatible discretizations. So we have done a lot of work on isogeometric analysis. So we sometimes use this NURBS, uniform rational B-splines, to describe the geometry. And we use also concept, for instance, for the adaptivity, which in this case is based on a quadtree or octree subdivision. You can do it in 2D, you can do it in 3D. So here are some features. First of all, the positive ones, it's relatively easy to implement. So for instance, in the deep energy method, the same of course applies to pins. You can just, for instance, define the potential energy. and then you're more or less done. So you can have a relatively complex coupled problem, and the implementation is relatively quick. And personally, I like the deep energy method because I'm working a lot in solid mechanics. So when you define now an energy, you directly have a consistent thermodynamic framework, like in the phase field approach to fracture, which you might not have when you have, for instance, like a pin approach. So you have, of course, also the opportunity to include experimental data, which is theoretically also possible in finite elements, for instance, in an inverse analysis. It's a unified framework for analysis and optimization, naturally accounts for stochastic effects, which is important for certainty analysis. It's also suitable for higher order PDEs because it's also a higher order continuous approximation. Of course, IGA or certain meshless methods fulfill this requirement as well. And maybe for some specific problems, particularly for high dimensional problems, you can have also quite efficient solution. Though for the problems I will show, actually the PIN or the DEM solution is actually not competitive to an associated FEM solution. So on the downside, we have a lack of robustness. So even if the forward problem or the problem which we want to solve is linear and well posed, when you solve it with a PIN or a DEM framework, you transform it to an ill-posed, non-linear, non-convex optimization problem. You have a relatively large amount of parameters to tune. And when I say lack of convergence proofs, I don't mean actually there are, of course, also convergence proof for approximation theory. But here we don't have something comparable as an FEM. So in FEM, for instance, we know when we refine the mesh, we make it finer and finer, then the error in specific norms gets smaller and smaller. This is deep neural network solution. Actually, the training points you see, this is not equivalent to a mesh or nodes in finite elements. In 1D, you can actually show that what is in a finite element, an element or node is rather a layer and a neuron in a deep neural network solution. That can be done for 1D with artificial neural network with one hidden layer. We have done it also in our one of the papers in 2020. So that is what I mean when I say lack of convergence proof. It's not when you basically add more neurons and more layers. That does not necessarily mean that the results will get better and better. Okay, so as I mentioned, that was like an approach to directly solve partial differential equations. So these neural operators, I think they are very interesting and they are very promising because they can actually solve not only one specific problem. So of course, let's say when you want to use a PIN, you solve one specific problem. And when you change then boundary conditions and so on, then you have, of course, to retrain the network. You can use concepts from transfer learning to maybe make the approach a bit faster. But this deep operator networks can be seen as a surrogate model. It consists of a branch net to encode the discrete input function space and the trunk net for encoding the output function space. And it can actually learn directly the differential operator. Actually, it's not really directly learning the differential operator. It learns the mapping between this input, the discrete input, and the output function space. So here you can solve directly a class of problems, not only one specific problem. So once a network has been trained, you have a solution relatively quickly. And there are several papers that actually report relatively good results for out-of-data predictions. So that means you train within a certain area, and then you have predictions outside the area, which I think for you have machine learning approaches, it's actually quite good for interpolation, but not so good for extrapolation. So that is a relatively nice feature, which I'm also very interested in. And the training in most of this deep net papers is actually done with this Gaussian random fields. Okay, so there are different network architectures for the neural operators. This is like taken from one of the first papers from George Kaniadakis. That is a stacked deep net and the unstacked deep net. So what is the difference? We have here a p number of branch nets and one trunk net, and here in the unstacked one we have only one branch net and one trunk net. So there are also other high fidelity network structures. Okay, so what I want to show you now are some numerical examples. So finally, you just need to define either the boundary value problem or the energy, and then you can directly solve it relatively quickly with either PIN, with DEM, or also with deep operator networks. And the deep operator networks, you can of course also generate the data from finite element simulations, for instance. Okay, so the first example is strain gradient elasticity. So we consider here an isotropic, gradient-dependent, linear, elastic, isotropic solid. So here we use the deep energy method. So most of actually the results I show are based on the deep energy method. And we tested also both deep energy method and pins. In most of the cases, the DM resulted in more accurate results, also in a shorter amount of time. So here we can define the strain energy density, which is not only a function of the linear strain tensor, but also of its gradient. So we have here the 2 Lamé constant, and then this last term is here related to the associated gradients, where C is now the strain gradient coefficient. So that is an example which is not that easily solvable with finite elements, because you need C1 continuity. Of course, it has also been solved with finite elements. There are some tricks as well to solve it. So the only thing what we need to do is we need to define the potential energy, which is the difference between the internal energy. So of course, if I go back, if you integrate now the strain energy density here over the volume, then you have here the internal energy. So the potential energy is just the difference between the internal energy and the applied work. And here maybe the like the slight difference to standard linear elasticity that you have here, this double spread, which basically are thermodynamic conjugates to the strain gradients. And of course, you need then finally also to set up the network architecture. You need to decide what optimizer you use, and so on and so forth. So training, of course, can still be an issue, can sometimes also fail. And of course, finding global minimum is always still also a problem here for this type of solutions. So that shows here now one example that is here the thick-walled cylinder, where we simply model only a quarter. We have here an external pressure of P0 and internal pressure of Pi. So you can see the external pressure in our simulations is set to 0. Internal pressure is set to 10 megapascal. We have then the inner radius of 1 micrometer, outer radius of 5 micrometers. We have here following material constants, and we change also the strain gradient coefficient from 0.01 micrometers squared to 0.25. And the good thing is we have here an analytical solution, so we can also test the accuracy for this simple problem. And that shows now for these material parameters the accuracy. Here you can see the exact solution. Then here you can see the predicted value, and here on the right hand side, that is the key, that is basically the pointwise error. You see the loss versus iteration, and the L2 error versus iteration. You can see we need to go back 10 to the power of 4 iterations to get a relatively small error. It's a relatively small error. Okay, so what we of course use, then we use, we want to solve several problems. We use some concepts of transfer learning. So the idea is to take knowledge from the previously solved problem, and we take this knowledge. We take now this knowledge for the next task. So the idea is to have here a higher learning slope, higher asymptote, and finally to get relatively fast or faster than before to a solution. And so we need, of course, have first one solution for one problem. So in this case, we have now a solution for an outer radius of 5 micrometers. So if we change now the outer radius to 3 micrometers, we can now use concepts from transfer learning. You can see here from the figure below that we have now like 1 or 2 orders of magnitude less iterations. So finally we come to a faster error by roughly the same pointwise error. So what we also suggested, instead of here we do the training in the physical domain, so we can use now concepts from finite elements. And I'm sorry, this is not correct. I think I should take it out from the slide. It's not the isoparametric or like domain, that is just a parametric domain, because iso means equal. So just a parametric deep energy method. So the idea is actually quite simple. Instead of doing the training in the physical domain, we have then a mapping between the reference and the physical domains, like in finite elements, and then we simply do the training in the reference domain. And with that, we can actually, when we have the same, for instance, PDE, we can, of course, solve a larger variety of geometric problems. You can, of course, use, for instance, also some domain decompositions and really divide the domain, which is in the literature often called X-pin, which has nothing to do with the extended finite element method. It's just you divide it into smaller domains, and you also naturally normalize the data, because the parameter space is always going from 0 to 1 or from -1 to +1, depending how you define it. So the idea is really simple. So instead of having the integral evaluated in the physical domain, you have to evaluate it in the parametric space. So there are two tasks to accomplish. One is the differentiation, and the other one is the evaluation of the integral. So one key task is to compute here the Jacobian matrix, of course. And here you can use any scheme, find a difference, whatever you like. So we have basically used, since we have done a lot of work on IGA, the concept of isogeometric analysis, and then we have defined first of all, like the knot vector. Based on that, we have then defined the B-spline. It's basically shown here, the figure on the left-hand side. I think if you're familiar with IGA, this figure probably is relatively familiar. Okay, so that is now an example of two standards. Linear elasticity is not overly exciting, so we have here the strain energy density for linear elasticity. That is here the constitutive equation. That is here our physical domain. That is our reference domain. And then we apply here our parabolic traction on the right-hand side, and fixed on the left-hand side. There's also an analytical solution for this problem, this cantilever beam problem. So, and here for this case, we also computed the relative errors in specific norms. In this case, in the L2 displacement norm and in the energy norm. Here you can see now the loss versus the iteration. If you compare to finite elements, you will see that maybe particularly the error in the energy norm is not overly impressive at 3%, maybe engineering accuracy. If you would solve it with a relatively fine FEM mesh, you get it down relatively quickly to machine precision, or at least errors in the order of maybe 10 to the power of -5, -6. But at least it shows that we can solve these problems also with this machine learning approaches. And as I mentioned before, what in fine elements you would usually do, you would look at the convergence plots. You have on the vertical axis error in a specific norm, on the horizontal axis then either the degrees of freedom or h, the element size, and you uniformly refine, and then you would look at the convergence rate in the asymptotic domain to see the performance of your FEM discretization. This does not make sense here so much, because for the reason which I explained at the very beginning, because refining the network structure does not necessarily mean that you get better results. So then, of course, we can also solve problems with have the same geometries in the parametric domain, but different ones in the physical domain. So that is again the thick wall cylinder here. In this case, we don't use gradient elasticity, but standard elasticity. We can use again concepts of transfer learning. And you can see again, if we use now this transfer learning, we can get the error, for instance, the results by 1 or maybe 2 orders of magnitude faster compared to without transfer learning. So what I've done or shown you before is basically deep energy method. Now let's short excursion back to PINs, physics-informed neural networks. I will apply it in a moment to heterogeneous amplifiers. As I mentioned before, one key task is to set up the network architecture, and of course, you need to get also good results for a variety of network architectures, not only once, or one specific one, but nevertheless, you need to somehow define it. So what we have done is it's based on actually 4 steps. Maybe by model training and validation, I think it's pretty obvious. So I think we have maybe 3 steps. First of all, we need to define the search space with the input parameters. So for instance, the layers, the units per layer, number of collocation points, and so on and so forth. Then you would do a sensitivity analysis to narrow down the search space. And then for the smaller search space, you can do a network architecture search to obtain the optimal network architecture. So to make it the long story a bit shorter, for all the problems we tested so far, the key input parameters were always layers of the neural network and the number of neurons per layer. So maybe you can save the first step and do the network architecture search directly only for these two most sensitive input parameters. And we applied it now, as I mentioned before, to groundwater flow in highly heterogeneous aquifers. We have here following governing equations, where that is here the hydraulic conductivity K. I hope you can read it. I know it's a bit small. H is a hydraulic head. And we have also tested different correlation functions. I don't want to be, too detailed, and just basically show you the network architecture search. So you can, of course, test different search methods, which of course takes additional time. So the best result was obtained by our Bayesian optimization. So in practice, you don't want to do it really for all these methods. You will just basically maybe use one, and then you can see we have here relatively the smallest error with the Bayesian optimization, and it takes 1,395 seconds. So of course you need to add this also on your total modeling time, because I think the training is also one of the longest time. And when you look at it for the 1D problem, the optimal network architecture is then for 2 layers and 37 neurons. It looks a bit different in 2D and in 3D. So on the right hand side, you see here the outcome of this network architecture search. So here in figure B, that's here the point which gives you the best results. And then we can test now this problem in 1D, 2D, and in 3D. So here that should be actually sigma square. We fix here the variance, and n is the mode number. And then we compare it also to find a different methods, which is basically somehow equivalent to a strong form, to a pin. And maybe just to the time and the error. So if you solve this problem with a finite difference method, you can see, particularly in 3D, we need relatively long, 1,245 seconds, which is still shorter than the network architecture search. But the error here is really too high, 5.7. It's more than 500%. I think in 2D, 1% error is, I think, still okay. Of course, 1D it's relatively simple. And if you compare that now here to the DCM solution, DCM is basically, we call it deep collocation method, which is nothing else but the physics-informed neural network. You can see the relative errors with or without transfer learning. They are always relatively small, 10 to the power of -4, 10 to the power of -3. That is here the dimension. You can see with transfer learning, it takes only 1.9 seconds. That includes the training. Plus, of course, then the network architecture search, 1,300 seconds. So we are, of course, just a little bit faster, slower than maybe here the finite difference solution, but at least for this specific problem, we are more accurate. Okay, so we now a little bit step back not step back, but a little change to the deep energy method. That is here now a phase field model for fracture. We have solved it also, as I mentioned, with the deep energy method. So that is the standard model from MIR presented in 2009. We have also implemented a 4th order phase field approach. So just for those of you who are not so familiar with it, we have here, first of all, mechanical equilibrium. So that is the divergence of the Cauchy stress, where G is the stress degradation function, which has this classical quadratic form. There are also some improvements. F is in the body force. We have then this von Neumann and Dirichlet boundary conditions. And then we have an additional variable, the phase field, for diffuse fracture. There actually has been relatively recently also now re-improved that there is gamma convergence, which really converges to discrete fracture. So we have here then an additional variable, the phase field. And so the evolution of the phase field is governed here by this equation. That is a standard 2nd order phase field model. GC is the critical energy release rate, an input parameter. L is the characteristic length, which you can relate to some mechanical properties like fracture strength and like critical energy release rates, tensile strength, Young's modulus, and Poisson ratio. So there are some, of course, assumptions behind it. And then on the right-hand side, you have here the positive projection of the strain energy density to make sure fracture occurs only under tension and not under compression. So that is here the strong form, and actually the strong form has been derived from an energy, and that is the beauty here of this approach of this form, also proposed from here, that this is a thermodynamic consistent framework. Here that is now the energy that depends on the displacement field and the phase field. So that is also what we use. We minimize now the potential energy. We have here D plus 1 outputs. D is like for the displacement. So D is a dimension. We have then D equal to 3 in 3D, equal to 2 in 2D, plus 1 output, which is the phase field variable. We use here a monolithic scheme. Of course, there are a lot of things you can play with. You can use even 2 network architectures. We used 1. We tried actually several options. Didn't find it advantageous to using 2 networks. But with a monolithic scheme, you can have much larger time steps or load steps, 10, sometimes even more, 50 times bigger compared to a staggered approach, which is standardly used in finite element analysis. The reason for that, for using a staggered approach, is that when you decouple the two energy, you have usually like a non-convex energy potential. When you decouple the phase field from the mechanical field, you have then 2 convex potentials. However, in our machine learning based solution, we anyways, even if we decouple it, we end up solving a non-convex optimization problem. So it does not make so much sense to use here a staggered approach. And of course, we also use then transfer learning techniques to speed up the simulation. So that is now one example where we use 3 hidden layers and 50 neurons. Very simple problem, can of course also be solved in 2D. That is a bar, or like here, like a cube under uniaxial tension, where the crack simply grows in a straight line. And that is here now the load deflection curve. It looks a little bit erratic, a little bit coarse, and the reason for this is because we can have this larger load steps. If you want to have a finer curve, you either use like a smoothing in the curve here, or you just have a smaller load step, and then you, of course, don't take advantage of this monolithic scheme. As I mentioned, we have also implemented the 4th order phase field model, which I didn't explain here, and the results, when you compare it, is similar, or a little bit similar. 2nd order compared to the 4th order approach. What you would usually do in fine elements, you would then refine the discretization to basically show it's independent of the discretization. But as I mentioned here before, that doesn't make here that much sense, because we don't have something like the fine element equivalent discretization. So we show only this low deflection curve for these 2 machine learning based solutions. But we compare that also to a FEM solution or to an IGA solution, and the results look similar. So that is here now another classical benchmark problem, the Bittencourt problem. So you have here a 3-point beam under bending, displacement control. We have here a pre-notch, then we have 3 holes, and depending on the distance between the pre-notch and the holes, you observe then different fracture patterns. So either the crack grows into the 1st, 2nd, or the 3rd hole. And we have solved it also with IGA. We can, of course, also use our IGA mesh for the deep energy method, which is shown here on the right-hand side. And that shows you now a solution where the crack basically hits here in the 2nd hole. We tested also some other scenarios. And that agrees also fairly well with results from the FEM discretization, also in the experiments. So that shows you know some results from our DeepONet. It was done by actually Sharin's postdoc, Ayan Chakraborty. So that is again like a plane under uniaxial tension. So you can see here on the left column that is basically the predicted, basically means that is what's obtained from the DeepONet. True means it's actually obtained from an IGA simulation, from a fourth order phase field model. So we used here this code to generate the data. So it's in this case a pure data-driven approach. And this shows here now the error in the phase field and then the error in the displacement in the vertical direction. So actually there has been also done some work by my former student Samdata Goswami in the group from George Kanyadakis. So I want to show some of the results she obtained, and that she published it also in a paper which unfortunately didn't write out here. But if you're interested, I can also send you the reference. So this is first of all, she has basically done it in two ways. One is purely data driven, and in the other way she also includes some information of the physics law into the loss function. She calls it then a variational deep operator networks. There are some other authors who basically have sometimes Fourier neural operators. They call it then a physics-informed neural operator. The idea is then, of course, similar. So this shows basically here now shear example. So that's of course here you can see the evolution of the shear crack for different positions of the crack tip. So the crack tip in the y direction is at 0.5, it's a horizontal crack, and in the x direction it varies between 0.2 and 0.7. There's 7 training samples. This is basically here on the left hand. This is here on the upper part, the predicted phase field and the predicted displacement field, and here that's the true value from the IGA simulation, and below you can see here the error. And okay, so that shows here now the difference between a data-driven and a variation deep operator. Data-driven means you only feed the network from IGA data. So you can see when you use 43 samples, you get here these results. And blue, this is basically the true solution from IGA using a phase field. You can see here some oscillations that is here in the displacement field that looks a bit awkward, shouldn't actually be there from the IGS simulation. And in red, you see here now the solution from the predicted solution from the deep operator network. If you include now some physics information, this variational deep operator, then you need only 11 samples, just show here again, and you can get actually a better approximation. And the very interesting thing is that is basically that you can also obtain relatively good results for out-of-data prediction. So here you have initial cracks between 0.55 and 0.375 position of the crack chip. You train the network with 20 samples, and then we test it. You can see actually the testing here is not overly good, but you test it with out-of-data distribution. Then you add another 20 training samples, test it again, another 20 training samples, and another 20 training samples, and then you can get down the error from 26% down to 3%, which is of course not overly impressive, but don't forget it's an out-of-data prediction, and it is, I think, within engineering accuracy, and once you have trained the network, the solution is obtained fairly quickly. So if this can be extended to more complicated scenarios where you can maybe also change boundary conditions, or maybe have like a fracture transition, not only like shear crack, but basically also like mixed mode fracture, then you can have also maybe drastic time savings. Of course, that is still ongoing research in many groups, and that is basically what we hope we can achieve that also in the future. And as I mentioned before, this is now a totally different topic, which I would skip and directly come to the end of my presentation. And thank you for your attention, and I'm happy to answer any questions.
Do we have any questions?
First of all, thank you for giving us such a lecture. And I'm James Fan, a master student from Prof. And one first question I want to ask is that there's two kinds of approach. First one is the domain approach, and second one is the reference physical domain and reference domain. So what's the pros or the cons of two approaches?
So I mean, that's when you call it parametric DEM. So I mean, there are of course like pins and DEM, and there's DEM and parametric DEM. So the key idea of this parametric DEM is that you train in the parameter space. The parameter space in geometry doesn't change, while you can have then a larger variety of geometries in the physical domain. And the other thing is that you automatically normalize the input data because it's put in the coordinates, and the coordinates can of course change dramatically when you have a physical domain, but the parametric domain is always between whatever 0 and 1, whatever you choose. This is the key advantage of this parametric.
Thank you for the rest.
I have one more question. I'm the PhD student in the Vision League, and thank you for your the talk. And I'm studying about the concrete structure. So like we can think about the microstructure to macrostructure. I think like the scale thing is different to think about the micro to macro. Is there any approach that we can think about like your research?
But of course, I mean, I cannot promise this for sure, but one application I have in mind is this computational materials design. So of course, then you have also size effects. So maybe we have then always the same geometry, like a cube, like an RBE, it's relatively similar or the same boundary conditions. And then the microstructure changes. So the idea is to train then the network for maybe certain material parameters, and then you get maybe relatively good results for like in distribution data, but then hopefully we get also relatively good results for out of data distribution predictions. So we maybe just simply change then not only the microstructure, but maybe even the materials. So instead of concrete, or so you have then polymeric composites. But if that really works, is still like an open question. That is what I hope it can achieve. Maybe it will never achieve it, but that is what I hope it can do at the end of the day. But I think it's still a long way to go there.
Yeah, other questions? Actually, it occurs to me that so you put new ingredient to your cooking now. Wow. This for me is even more complicated. But as I understand, it seems that for your training purpose, you have to build some the left hand side and then also right hand side, and then. So you try different sets of the field variables for the training purpose, and then once you training it, then you use the training set as the starting point for the new program.
That is of course in the case particularly for the scheme operator network. Yeah. So you basically train then this neural operators. And then
how to say different from the neural operator and then the point collocation?
Well, this pins or this DM, they can solve only one very specific problem. You define like a problem, bounding conditions, geometry, and so on. You solve this problem, it's done. You want to solve now a slightly different problem. So, for instance, you apply now on your load, or you just basically make this problem just bigger. Then, of course, you have to retrain the network. You get new hyperparameters. You can use concept of transfer learning, but even then, I think when you compare to fine element solutions, it's not really much faster. And I think it's not so easy for like the applications we have. We don't have usually very high dimensional problems to make this approach competitive to FEM. But with this deep nets or general neural operators, there are other like spectral neural operators, wavelet neural operators, and so on. So there's also like the discussion which one is the best. Here you can solve a class of problems. Of course, the key into is still training. You need to train, particularly when you have relatively complicated problems. You need a lot of training data to train this network, and then you could have maybe relatively good out of distribution data prediction. So you train it for one problem and you can solve already some other problems.
So this approach is kind of self-accelerating.
Exactly, yeah.
As you have more data.
Exactly, yeah. It's basically, I mean, usually we don't have really large data and like the problems I solve.
So as long as you have same topology, then you can use previous training. Very interesting.
Yeah, I mean, hopefully, maybe you can even change the geometry in it. But I mean, this is basically not really clear. Let's say, what I have seen so far in the literature, the out of distribution data is not that much. Like I think sometimes you, for instance, train it for one material parameter from let's say 0 to 0.9, then you just change this one parameter to 1, and then you get good results. But it has never been tested for like very complicated problems, and there are of course still a lot of theoretical issues. So one is like they call it Venus, I think representation equivalent neural operators that actually ask the question: is it actually a real neural operators? Can you actually really like learn the operator? Because sometimes you just learn the mapping between the input function space at discrete points and then the output function space. So there are like a lot of theoretical questions, but of course there are also a lot of applications, and it's of course relatively new. So when you look at the problems they solve, they are not most of the time not that impressive, like, compared to like very complicated geometries and so on, which have been solved already with finite elements and IGA, where sometimes you can see an entire submarine immersed in water. So this type of problems have not been solved with this type of techniques, but of course they are also not that established. I mean, they're new.
Is there any other studies in which people develop some artificial neural network supporting constitutive models?
Yes, but it's a completely different direction. I think there's Michael Ortiz is going in this direction. So instead of having now like physics like based constitutive model, they get it from
without having the background of some physics.
Yeah, I mean, of course, I think finally there are some physical laws that you would like to fulfill, right? Yes, like, for example, first technical law of thermodynamics would be good if that is also fulfilled by your approach, and if you just plug in some data which violates some physics, I think that is not so good. So I think you need to also request or put this information into your constitutive model, or in this case here into your formulation. Personally, I think I like this approach somehow a bit more than this direction of the starter-driven constitutive model. So maybe it's also a matter of
It's
taste.
physics, not pure data.
Yeah. This is very. I'm very interested to realize that you are still in the front line of research. Thank you very much for your presentation. Let's move to the second talk by Professor Rabczuk.